The temperature is dropping rapidly. Could a new disaster strike Mars's supervolcano, Olympus Mons? From base to summit, it rises 26 kilometers, almost 3 Mount Everests stacked on top of each other. It's not just the tallest volcano on Mars, it's the largest in the entire solar system. And there are good reasons to believe it's not dead. But before we can figure out whether this giant could awaken, we need to grasp one thing. Olympus Mons is a mountain you can't really see. The biggest features often have a strange effect. They slip right past our perception. We easily notice things that fit within our field of view, a rock, a tree, or a building. But when something stretches beyond the horizon, our brain stops recognizing it as a single object. In this way, Olympus Mons is, to me, the most disorienting landscape in the entire solar system. At the base of the volcano lies a cold, dusty plain. A reddish haze settles over everything here. Beneath your feet, frozen lava flows stretch out, some smooth and glass-like, others cracked, rough, and brittle underfoot. These flows spread out from an unseen summit for hundreds of miles, as if the lava didn't just flow for days or months. But more on that later. Every step feels different than it would on Earth. Mars's gravity is only 38% of Earth's. Your body weighs just over a third of what you're used to. Movements slow down, almost floaty, but this strange lightness is deceiving because nothing around you offers any protection. At the base, the atmosphere is already stretched to its limit. Pressure here is about 160 times lower than Earth's. As you climb higher, it thins out even more. Temperatures plunge by tens of degrees. At the summit of Olympus, there's practically no air at all. This isn't an atmosphere anymore. It's the edge of open space. And here's where the real paradox begins. Standing on the slope of the tallest mountain in the solar system, you can't actually see the mountain. The slope is so gentle and the base so vast that your eyes catch only a slightly tilted plane stretching to the horizon. No peak, no ridge, not even a hint of a summit. Your mind refuses to piece it together as a mountain. The horizon looks strange. Mars is smaller than Earth. Its radius is about half as long. The planet's curvature is much more pronounced here. The edge of the world doesn't stretch off into the distance. It falls away, as if the surface is sliding downward in every direction. Simply put, you're standing on something too massive to be a mountain, yet too small to be a planet. None of your earthbound instincts work properly here. But to understand how this landscape formed, this place that warps your very sense of space, we have to travel back to a time when Olympus Mons was thought to be something entirely different. Milan, 1877. Giovanni Schiaparelli, director of the Brera Observatory, pressed his eye to the refractor's eyepiece and spotted a bright white patch on the disk of Mars. It was steady, clear, and appeared night after night in the exact same spot. By the end of the 19th century, astronomers had cataloged dozens of surface features on Mars, but this one stood out, too bright, too consistent. Schiaparelli named it Nix Olympica, the snows of Olympus. The reasoning made perfect sense. A bright spot near the planet's polar caps probably meant snow on a towering mountain, kind of like how Kilimanjaro looks from space. The idea caught on right away. For nearly 100 years, no one seriously challenged it. A century is a long time, long enough for a romantic misconception to become a textbook fact. November 14th, 1971. The Mariner 9 interplanetary probe enters Mars orbit, becoming the first artificial satellite around another planet. Engineers in Pasadena wait eagerly for the first images of the surface. The cameras switch on, but they show nothing. Mars is engulfed in a massive dust storm, one of the most intense ever recorded. The entire planet is shrouded in a reddish haze. Its terrain, craters, and canyons vanish beneath a layer of suspended dust tens of kilometers thick. But here's what didn't add up. Above that haze, the storm that had swallowed an entire planet, 4 dark spots stood out, 4 peaks that dust couldn't hide. One of them was the feature known for nearly a century as the Snows of Olympus. That's when a question hit planetary scientists like a punch to the gut. If the dust layer rose more than 20 kilometers high, and these peaks still stood taller, then what exactly had 19th century astronomers mistaken for a snowcap? The storm finally settled in a few weeks. The dust fell slowly, layer by layer, like a curtain lifting from the bottom up. When the surface finally emerged, the truth became clear. There was no snow. Instead, there was a caldera, frozen lava flows, a shield volcano profile familiar to any volcanologist. The so-called Snows of Olympus wasn't a snowy summit at all. It was a colossal volcano. Scientists renamed it Olympus Mons, Mount Olympus. Then they measured its size. 26 kilometers from base to summit. Mount Everest stands at 8.8 kilometers. Imagine stacking 3 Everests on top of each other, and you'd still have some height left over. But there's a stricter number. 21.9 kilometers above the areoid, which is Mars' equivalent of sea level. Why call it an equivalent? Because Mars doesn't have seas anymore. Yet the very need to invent a sea level for this planet hints at something deeper, a story we'll return to later. The volcano's base stretches 624 kilometers across. Put it on a map of Europe and it would cover all of France. In other words, one mountain the size of an entire country. For nearly a century, humanity gazed at the largest volcano in the solar system and saw nothing more than harmless snow. But when the dust finally settled, both literally and figuratively, a new question emerged. What force allowed a single volcano to grow so massive that it pierces its own atmosphere? The answer starts with lava. Not the kind you see in disaster movies, scorching fountains, ash explosions, smoke columns stretching to the sky. Olympus works differently. It's a classic shield volcano, built by the slow layering of very fluid basaltic lava. No explosive eruptions here. The magma simply flowed out of the vent, spreading tens of miles around, cooling, while the next flow settled on top. Layer after layer, millennium after millennium. Imagine pouring hot chocolate onto a saucer. Each new pour slightly widens the puddle, raising its center just a bit. That's why Olympus has such a gentle profile. Its slopes barely tilt between 2 and 5 degrees. Standing at the base, the climb feels almost flat. The mountain is so broad and low that it looks less like a peak and more like a continent, gently lifted up. But here's the puzzle. Shield volcanoes exist on Earth, too. Take the Hawaiian Islands. They follow the same pattern. Fluid lava, gentle slopes, no catastrophic explosions. Mauna Kea rises about 10 kilometers from the ocean floor. That's an impressive height. Yet it still falls far short of Olympus Mons. So why don't Earth's shield volcanoes reach the colossal size of those on Mars if they share the same underlying process? To answer that, we need to look beneath our feet, literally. Earth's crust isn't a solid block. It's broken into tectonic plates that drift. Slowly, almost imperceptibly to us, but relentlessly. Iceland offers a clear example. The North American and Eurasian plates pull apart right beneath the island, moving at about 2 centimeters per year. That's roughly the speed at which your fingernails grow. Over 1 million years, that adds up to 20 kilometers. Over 100 million years, 2,000 kilometers. What does this mean for a volcano? Here's the idea. Deep within Earth's mantle, there are hot spots, areas where magma rises toward the surface. A volcano forms directly above one of these hot spots, but the plate beneath the volcano creeps sideways. After a few million years, the volcano drifts away from its magma source, like a suitcase on an airport conveyor belt. Its eruptions stop. Then, a new volcano forms nearby, right above the same hot spot, and that one drifts off too. This is how chains form. The Hawaiian Islands exist for exactly this reason. Every island is an old volcano, shifted from its original spot. Simply put, Earth's volcanoes have a built-in growth limiter. Tectonic plates keep them from staying put for too long. Now let's look at Mars. Mars has no tectonic plates. Its crust is completely still. Not just temporarily, this planet likely never had plate tectonics like Earth does. And here's where the key mechanism explains everything. A hotspot deep in Mars's mantle pushes magma upward. The magma reaches the surface, flows out, and cools. But the crust doesn't move, not at all. The next flow of lava hits the exact same spot, then the next and the next, for billions of years. Each new layer stacks on top of the last. The mountain keeps growing, and nothing shifts it away from its source of magma. On Earth, a volcano gets magma for a few million years, then shuts down for good. On Mars, the same volcano can pump lava from a single spot for 3.5 billion years straight. Earth's living, shifting crust creates scattered clusters of small volcanoes. Mars's dead, frozen crust builds up just one, an enormous one. The longer the crust stays still, the more mass piles up in a single spot. That spot grows heavier and heavier on the surface. Meanwhile, the planet's internal heat, blocked from escaping through cracks and plate boundaries, searches desperately for any exit. And it finds the same channel that has been active for billions of years. But Olympus Mons doesn't stand alone. This is crucial to grasp right now, because without it, the scale of the disaster slips away. Olympus Mons rises at the edge of a colossal volcanic province called Tharsis, or the Tharsis region. The Tharsis Dome towers 10 kilometers above Mars's average surface level and covers about a quarter of the entire planet. A quarter. To put that in perspective, on Earth, one volcanic region that size would stretch across all of North and South America combined. Spectrometric analysis reveals that the rock here is basalt, rich in iron and magnesium. It contains pyroxene and olivine minerals, typical of deep molten rock. Dark, dense, iron-heavy lava that once flowed like water down a steep slope. At the heart of this vast dome lies a chain of 3 shield volcano giants. Olympus Mons stretches 18 kilometers high. Pavonis Mons reaches 14. Olympus Mons tops out at 17.5. Each one towers 2 to 3 times higher than any mountain on Earth. Just the caldera of Olympus alone spans 110 kilometers across, a crater large enough to fit Lake Superior inside. Along the northern edge of the Tharsis region, Alba Mons rises, a completely different kind of giant. Alba isn't tall, but its lava flows extend 1,350 kilometers from its center, covering an area nearly twice the size of Turkey. It's the largest volcano by surface area on Mars, a broad, sprawling shield volcano that never formed a true mountain because its lava was too fluid, spreading out too far. And now, the consequences. This entire mass, the basalt flows of Olympus, the triple chain of shield volcanoes, the sprawling Alba Plain, pressed down on the crust for billions of years. The crust didn't shift. It didn't redistribute the load. It didn't carry the excess weight into subduction zones. It simply bore the burden. Until, at some point, it gave way. The immense weight of the Tharsis bulge fractured Mars's crust. Not just a small crack at the base. Fault systems spread thousands of miles from the epicenter, like cracks spidering across a windshield after a rock strike. Except here, the rock weighed quintillions of tons, and the glass was the crust of an entire planet. In other words, volcanic activity in one region warped the surface of an entire hemisphere. Mars lacked plate tectonics, but it developed fractures that, on Earth, only form along plate boundaries. Now, let's return to Olympus, specifically its summit. At the very top lies a depression. Well, not exactly a depression. A caldera, a massive crater formed when the magma chamber beneath the volcano emptied after eruptions, causing the roof above it to collapse inward. It stretches 85 kilometers long and 60 kilometers wide, plunging as deep as 3 kilometers. This crater could fit a small European country inside it. But the size isn't the strangest part. Within this main caldera, there are 6 distinct craters layered atop one another, like rings on a cross-section of a tree trunk. Each one marks a separate phase of volcanic eruptions. The magma chamber would refill, the volcano would erupt, the chamber would empty again, and the roof would collapse. Then the cycle repeated, just slightly offset each time. 6 times in total. 6 nested collapses, one inside the other. At the base, there's a different kind of mystery. The slopes of Olympus Mons are almost flat, with an average incline of just 2 to 5 degrees. This is the result of that incredibly fluid basaltic lava, which flowed for hundreds of miles. Standing on such a slope, you wouldn't even feel like you're climbing. But down below, where the slope ends, there's a sheer cliff. 6 kilometers of vertical drop. A wall taller than the distance from sea level to the summit of Mount Kilimanjaro. The area around this cliff, known as the aureole, is riddled with folds and fractures left behind by ancient landslides. Chunks of the slope breaking off and sliding down like dough slipping off the edge of a table. Where did this cliff come from? One theory stops you in your tracks. Maybe it was a shoreline, the shore of an ancient Martian ocean. Lava from Olympus Mons flowed downward and crashed against water. The water cooled the lava instantly, freezing basalt into a vertical wall. The ocean has long since vanished, but the wall remains, a scar marking the boundary between 2 vanished worlds. Here's what puzzles scientists. The surface of these solidified lava flows looks surprisingly fresh. They show almost no signs of meteorite impacts, as if the last traces of molten rock settled here just moments ago. Looking at these colossal scars, the fractured crust, 6-kilometer cliffs, and overlapping calderas, you might think you're staring at a monument to a long-lost era. But that impression is misleading. Planetary scientists have a way to determine the age of a surface without ever touching it. The method is elegantly simple. Count the craters. Space is a shooting gallery. Meteorites have been bombarding any body without an atmosphere, or with a thin one like Mars, relentlessly and evenly for billions of years. The older the surface, the more impact scars it bears. Ancient Martian plains are so densely cratered that the marks overlap each other. Now, take a look at the upper layers of Olympus Mons lava. The surface of this volcano has surprisingly few impact craters. So few, in fact, that it's the first thing you notice when analyzing orbital images. Smooth lava fields that seem almost wiped clean, as if someone polished them with a cloth. And here's the question that haunts planetary scientists. If Olympus Mons is a dead relic, frozen in time billions of years ago, along with Mars's magnetic field and thick atmosphere, then where are the scars from 4 billion years of meteorite bombardment? They're missing. Or rather, there are far too few for a surface that should be dead. Counting crater densities and calibrating with lunar samples give us a clear number. Experts estimate that Olympus Mons last erupted just 25 million years ago. 25 million. That sounds like forever. But what does that mean in scale? Mars is about 4.5 billion years old. If we compress the planet's entire history into a single calendar year, those 25 million years fall within the last 2 days of December. Lava flowed down Olympus Mons on December 30th. On the geological clock, that was just the day before yesterday. A dead planet, a cooled core, a frozen desert without a magnetic field. It seems like everything ended long ago, and for good. Yet the surprisingly few craters on its summit tell a different story. The volcano hasn't died out. It's merely asleep. Scientists have a solid reason to believe that Olympus Mons could still be active, capable of erupting again. Not tomorrow, not in 1,000 years, maybe millions of years from now. But on the scale of the volcano's sleep, which has lasted just 2 days, that's a blink of an eye. Here lies the paradox at the heart of this story. Mars, a planet we've always thought of as dead, cold, dry, a lifeless rock. Yet the tallest mountain in the entire solar system stands on its surface, and by all signs, it's just resting between 2 breaths. This dead planet holds a sleeping volcano, younger than most mountain ranges on Earth. Mars hasn't finished its geological story. It has simply fallen silent. Beneath 22 kilometers of solid basalt, molten magma may still be waiting with no rush to rise.